Okay, take it away, Gordon.
All right, let me get out of there. There we go. Hello, guys. Gordon Rosner here, your president of East Valley Astronomy Club. So here's the agenda tonight. Usual type of stuff, except look at that third item down there, officer elections. Big thing coming on up. So we'll chat about that for a little bit. Then we'll go into the usual club olds, because there's been no changing. We have a member presentation tonight. You know Bob Buchheim. He has given a couple presentations for us before, so he should be familiar to most people. He's got a fantastic personal observatory too. And he's enticing everybody with something you don't see every day. And matter of fact, he has not even told me what that is. And then our main presentation, Dr. Nathan Williams on NASA and JPL, talk about the Mars helicopter. What's going on in the first 6 months? So we have a great presentation, a couple of great presenters tonight. And Steve of SAC is going to jump on in for a moment to talk about an event that's coming on up. So, matter of fact, Steve, why don't you jump in right now and tell us about that?
Okay, I will. I want to talk quickly about the Grand Canyon Star Party that happens. I think this is like the 27th year or something like that. Maybe Tom can help me out there. But I'm coordinating the North Rim, and I'm taking reservations for volunteers that have their own lodging at the North Rim. If you get a reservation at the North Rim and bring a telescope, we can get you in. And starting at January 1st, we'll have free campsites for those that will stay for the whole week. All the details are on the Saguaro Astronomy Club website, saguaroastro.org. Under the events tab, you'll see Grand Canyon Star Party 2022. That's happening June 18th to the 25th next year. And it's been canceled the last couple of years because of the pandemic, but we're got to do the planning whether we're having it or not. So if we get our volunteers in and everybody gets all set up, then if they run it, then if they figure out a way to run it safely, then we'll be doing it. But I need to have volunteers ready to go, just in case everything works out. So you can send me an email. My contact information is on the saguaroastro.org website, and it's also in the events tab under Grand Canyon Star Party. So if you're interested in doing public outreach with your telescope for the whole week and camp for free at the Grand Canyon North Rim, we'd be more than happy to have you there. I appreciate you guys, and I hope you get back to me. Thanks a lot.
So I put the link in the chat message, Steve, that takes you right to the Grand Canyon Star Party 2022.
Yeah, I'm not seeing that.
So if anybody like to get more information, there's the link, and I think it has your contact information as well, Steve.
Okay, I'm not seeing it, but where's the chat part?
Yeah, it's at the bottom of your Zoom screen.
There it is. Okay, yeah, I'll put the link in right there. There it is. There you go. That'll take you straight. Oops.
All right, good. Thank you, Steve, for that reminder of a great event coming on up. All right, we'll get started here. And as usual, everyone, I hope everyone lives long and prospers. Introductions. I put this screen up all the time. Every meeting. Here's your leadership team and your administrators. The column on the left are those who actually perform administrative type of functions. They are elected, right? The administrators on the right, they're assigned. Notice the property administrator. James Yoder has joined us as the property administrator. So all that took was was an approval by the board of directors, which is all those people off on the left. And of course, James got 100% approval from everybody. So James, thanks for stepping up, and we know you will do a great job. So the most important member of the club, obviously, is you. Officer elections. Yeah, let's start thinking about the elections. Next year's club officers. All the officer positions will be open for nominations. All of them. President, vice president, treasurer, and secretary. Those are the administrative officers, right? And then the board of directors. All 5 of them are up for election. And why all of a sudden everybody's up for election? Well, remember last year, the sitting leadership team agreed to just go another year as they are because of the pandemic, because of the uncertainties, things like that. We didn't want to change driving the wagon right in the middle of all of that. So they all agreed to maintain their seats and to keep the club going. And wow, they sure did a great job and continuing to do a great job. So officer elections are coming up. And remember, they start during October's meeting. If anyone has a question about any of these positions, write me a line. You can go to the club website, the first page down at the bottom. It says contact president. Just write a little email to me with your question and I'll get back with you. But the president, of course, is the one, basically I say, the president just makes sure everyone else is doing their jobs, which I have the easiest job of all because everyone has been doing such a fantastic job. I also, if there's a vote and there's a tie on anything, then the president has the vote to break that tie. The president also is involved with the treasurer. If ever there's large expenditures, then the treasurer and the president signs off on the checks. The vice president's main job is, in case I can't make it, then the vice president takes over. Vice president also makes sure that we have a presenter for each of the meetings. Now, he may not beat the streets looking for him, but he may use other people. Like for instance, Tom Palakis. Tom Palakis is a fantastic resource for the club, and he's been helping the Vice President, Tom Mosden, with getting these great, fantastic presenters that we have. Tom Mosden, our Vice President, just happens to be a PhD in astrophysics who works at ASU. So he's got a good pipeline. And, any other vice president coming on up, I'm sure that you'll be able to tap into that pipeline of his. The treasurer, of course, writes the checks, takes the money. Anyone who's interested in any kind of financial juggling around, any budding CPAs, of course, the treasurer keeps the books, keeps a list of members, takes the money in from memberships, writes the checks. What are the checks? Well, we have some standing type bills. Our internet providers, we got to write a check to them. Our insurance, because we still are a club, he writes the checks to there. And then if anything comes up that the board of directors say, hey, we want to buy something for the club, and it has passed the vote, then the treasurer writes the checks. And the whole system is audited once a year by the administrative team. And also the treasurer, when we get together, if you recall, gives a presentation of the status of our funds. And right now we're doing fine. The club is doing fine right now. We're paying the bills. The secretary takes notes. Like every one of these meetings, Wayne takes the notes, publishes those notes. Any kind of of special meetings that the board of directors do. Wayne takes the notes and then puts them, files them basically to make sure they're recoverable. So all of those people are open, all of those seats. So if you have any inclination at all to be a part of the leadership team of the club, by all means, come on, join on in, because all of these people's positions are open. Now, if you say, oh, I don't want to do that. Oh my gosh, what happens? We're in the middle of a pandemic and we're getting our way out of it. What's going to happen in the next year? Remember, we have processes that we've developed for the pandemic. We also have processes pre-pandemic that we can just bring back. So really, all you have to do is maintain what we've already had. So it's not a big deal. Don't be concerned about that. And plus, all the other officers, we're always, even if we're not holding positions, we're always, there for questions or help anyone out for sure. So remember, nominations will be open during the October general meeting and will continue for just a few days afterwards, because we want to get it all in the newsletter, all the people in the newsletter, so we can actually do the elections in November. So any questions, just give me an email through the link. If you want to volunteer for a position, talk to any of the club members. I'm sorry, not club members. I'm sorry, the officers, and they're available through the links also in the website. So if you want to volunteer, either let me know or any of the officers know. So club news are usual holds. So Greco still remains open for private viewing only. We are not open to the public yet because of the uncertainties going on with COVID, but the private viewing that Claude Haynes has been doing, been running fine. They're small groups, less than 6 people, and that's been going okay. All other EVAC personnel contact events still remain canceled, so there are no outreach events going on. There are no public star parties. Those are still on hold. We don't know when we're going to open up. We thought that we may be opened up by now, but then came the COVID uncertainties, so we're still on hold. Don't know when we're going to get off of it. Member presentations, remember? Anyone that wants to make a member presentation, let me know, and you can join on in. Bob will have a very good example of a member presentation today. Member articles, any articles about your adventures in astronomy, and you want to write up a page or so about it, do so and just send it to me via the president's link, and we'll get you in the newsletter. Remember that these monthly meetings are being recorded, and the link provided on the EVAC website. So if you want to see it again, or you know someone that missed it, just go into our website under the events, and in there, there'll be a link for this entire meeting being recorded. So our next EVAC meeting is Friday, the 15th of October. Look at that, the 15th of October. Just so works that that's the 3rd Friday of the month on the 15th. Whoa. Main presentation will be by Tyler Ritchie Yao, a PhD candidate at ASU, and he'll be talking about planets orbiting around K-stars for super habitability. So that will be interesting to see what he has to say. So our member presentation, Bob, something you don't see every day. So I can't handle the expense anymore. Bob, jump in and let me know what I don't see every day.
Okay, thank you, Gordon. You have to stop sharing so I can start.
And let's see.
Perfect.
All right.
Was on my screen moments ago. Okay, you seeing a blue screen with a title?
Not yet.
Why not?
Here, it's coming up.
Okay, that's
There we
your
go.
internet connection.
Oh, yeah.
Okay, I've got 3 items that are going to appeal only to the geekiest of our members. The first one is if you're one of those people who's fascinated by cosmology, and if you watch the literature, you might remember this article. In 2018, these astronomers reported the discovery of streams of stars and a few globular clusters that moved a little bit retrograde around the Milky Way and also had a unique chemical signature. They proposed that in its early history, our Milky Way galaxy collided with and devoured a dwarf galaxy thought to have been slightly more massive than the Small Magellanic Cloud, about a quarter of the mass of the proto-Milky Way. They called this hypothetical dwarf galaxy Gaia Enceladus for reasons that I do not remember. Now that's sort of interesting, but here's what it has to do with us. I recently ran across a short article in the research notes of the American Astronomical Society reporting that using the Gaia satellite's exquisitely accurate measurements of stellar parallax and proper motion, these authors were able to identify some of the individual stars that almost certainly are leftovers from that merger, stars that originally formed in the Gaia Enceladus galaxy and were captured into our Milky Way during the merger. These stars from another galaxy are distinguished by their unusual velocity vectors, which are quite different in both radial and circumferential velocity around the Milky Way, and also by their very low metallicity, which correlates to great age. The point of that little research note is that a couple of dozen of these alien stars are bright enough to be easily observable by backyard astronomers, bright enough to see in binoculars. 4 of them are up in our night sky right now. And here's where they are. The authors of that note suggest that observing these stars and knowing their backstory might be a way to spice up an outreach observing session with school kids, and they make unique additions to the life list of amateur astronomer observers. A star that was born in another now extinct galaxy, that's not something that you see every night. Now, if this idea sounds just a little familiar, you may also recall Steve Gottlieb's wonderful article in the October Sky and Tell about the Sagittarius Dwarfs spheroidal family, where he points to several globular clusters and planetary nebula that are also associated with a tidal stream. But that's from a different beast that suffered a similar fate to Gaia Enceladus. So, hey, it's amazing the things you can see just by looking. Item number 2. In recognition of the importance of amateur astronomers to science, to public outreach, and to policy advocacy, the American Astronomical Society is making a renewed effort to engage with our community. That includes the amateur affiliate membership in AAS, which is now open to everyone who supports the mission of the American Astronomical Society, wants to participate, and would enjoy meeting the people who are making the discoveries. It's a reduced cost. I think it's $53 a year, which is a real bargain compared to normal full membership. And it comes with many of the benefits of full membership. One of the key things is AAS no longer requires that amateurs be sponsored by a full member in order to join. So for details, go to the website there, aas.org/join. Another change that is in the near future for the American Astronomical Society is that the journals are moving to a full open access model. Starting next year, you'll be able to read the current research and astronomical journal, astrophysical journal, et cetera, without being a member and without going through a paywall. So if you're into that kind of thing, good to know. Number 3, but definitely not least, the American Association of Variable Star Observers just this week announced that this year's meeting will be run on a hybrid model, welcoming participants both in person and online. If you're curious about stellar spectroscopy, the spectroscopy workshop is going to be a great event. There are presentations and activities aimed at novices, at experienced observers, and educators. The annual meeting has scheduled an impressive array of keynote speakers, plus professional and amateur presentations describing observations and research results in the study of variable stars and exoplanets. For details, click on the link down there, aavso.org 110 annual meeting. 110 because this is the AAVSO's 110th anniversary of being the premier citizen science organization in astronomy. So thank you for your attention. I'll fade to black and I'll put into the chat the identity of those 4 alien stars that you're going to go look for tomorrow night. Thanks, guys.
All right, Bob. Hey, thank you. Thank you again, Bob, for another great member presentation. Now, this is a good example, folks, of what member presentations are about. So anyone that wants to give some information about what's going on, let me know and we'll squeeze you in. So Bob, we look forward to another presentation from you in the future. Thank you very much. And what I will do is I will hand it over to Tom Marsden, who will talk about our main presenter. Tom.
All right, thanks, Gordon. So I'm really excited. We have record attendance today. So far, we've hit a peak of 91. I hope we get a few more to hit that magic 100 mark. But this is definitely record attendance. So good job, Nathan. Yeah, both Nathan and I started our PhDs at Arizona State in the CC, School of Earth and Space Exploration, in 2011. Nathan finished a year earlier than me in 2016. And five years, got a job at JPL. And 5 years later, he's driving Mars rovers and commanding helicopters on Mars. So pretty cool. Good job, Nathan. So a little background about Nathan. He's a planetary geologist specialized in remote sensing of planetary surfaces, particularly relating to tectonics, structural geology, surface morphology, and landform evolution. His dissertation focused on assessing the distribution, causes, and timing of lunar tectonism. As a postdoc, then as a scientist and science system engineer at JPL, he has been conducting landing site selection, characterization, and geologic assessments for NASA's Mars 2020 rover Perseverance. The Mars 2020 rover, helicopter, and Mars Exploration Rover Opportunity, InSight lander, Mars Sample Return lander, and Fetch rover, and SpaceX Red Dragon and Starship landers. It took quite a while for Nathan to get a free Friday to come and talk to us, but here it is. Here's that Friday, so please welcome Nathan.
Oh, thank you. Yeah, it's great to be here, be able to share this with you. Yeah, it's been quite a wild ride, especially these past 6 or 7 months, but even beyond that, getting everything ready for the rover, for the helicopter, and the brand new missions on Mars. So can I just get a check from somebody that my screen is visible?
Looks great.
All right, excellent. So I wanted to give an overview of what the first 6-ish months have been like on the red planet for Ingenuity, our little Mars helicopter, and pretty much all the pictures and videos that I'm going to be showing tonight. We released all those almost immediately to the public on the mars.nasa.gov website. So you can follow along with that whenever you want to see the raw data, even stuff that isn't highlighted on the Twitter feeds and whatnot. It still gets posted there, so you can see all the images and video that we're taking as soon as it is processed internally. And oftentimes it's within like single-digit minutes of when the science team gets it too. So you can be right there at the forefront, seeing the stuff right as we're seeing it. Oh, I'm getting an earthquake alarm. It is fun living in California sometimes. Give me one moment. One of the joys of being a geologist, I have these alerts set up. Let's see. I'm going to wait another probably 45 seconds. Magnitude 4.6, a little bit south of here. That's fun. Yeah, so my background is actually in tectonics, and when I was at ASU, I did my PhD looking at tectonics on the moon, looking at all the stuff happening there. But I mostly look at rocks and surfaces on planetary bodies, and Mars certainly has a lot of really cool geology. So that got me into looking at stuff with rovers, working on the Opportunity rover, and then doing so especially with images to understand how things are relating spatially. And then the opportunity came up to work with the helicopter, be able to get a different perspective. Most time when we're just driving on the surface with a rover, we can see a lot of really cool geology that way. But having an aerial perspective, I think, just gives you a bit of a different view of things. And so looking down, we feel a little bit of the earthquake waves now, not so bad yet. But being able to look down, you can really see things. You don't have occlusions. You can get a really good understanding of where things are spatially. That with a rover may be a little bit more difficult sometimes. So it's been really cool to have its perspective, and it sort of blends between seeing things from the ground and really high resolution, but you're right up in front of it and seeing things at an angle and distance, versus if you're looking at satellite images from space. Those are much lower resolution, but you get great context. And an aerial platform can really merge the difference between the two. All right, well, nothing seems to be falling down right now, so I guess I'm going to move on to the next slide. So the goal of the helicopter mission, number one, is to fly. We've never flown a powered, controlled aerial vehicle on another planet before. There's been balloons on Venus, and we've had single-use vehicles like the sky cranes that land the rovers that hover with rocket exhaust. But we never had a heavier than air powered vehicle that we can use on the surface repeatedly. So this is all brand new stuff. It's challenging on Mars because the atmosphere is only like 1% as dense as it is here on Earth. And that varies with the seasons too by quite a bit. It's thankfully has a lower gravity. It's unfortunately a lot colder. And while it's really far away, you can't just take your remote control and fly it around, because by the time you would send the commands, it would take several minutes for those commands to get there and then start doing whatever you told it to do. And if it starts having an issue, if you tell it to stop, it also takes several minutes for those signals to get there and for you to actually be able to respond to anything that happens. Now, the way that the vehicle is set up is we have, it's decent size. So the blades are about 1.2 meters in length, tip to tip. So it's not a small vehicle, but the entire thing has been built to be really lightweight. The entire spacecraft itself is only, it's only 1.8 kilograms. So on Earth, that's a little bit less than 4 pounds. And on Mars, with this lower gravity, it only comes out to about 1.5 pounds, pound force. So really lightweight. So that helps with the lower, the thinner atmosphere. The other thing that helps is we can spin the blades of the helicopter so much faster than we can here on Earth. On Mars, we've been spinning them at about 2,500 RPM, which is 5 or 6 times what they normally do here on Earth. And we've just recently, in the past literally day, we've gone up to 2,800 RPM. So by the combination of the lightweight, lower gravity, and the high spin rate, plus just having really huge blades, we're able to generate enough lift in theory to be able to fly. But no one's ever tried that live before. So, well, this is a technology demonstration. Let's try it. So for the helicopter itself, here's just the quick overview of it. It's very simple. The blades are most of it. Got to generate that lift. We have a solar panel on top. That is what that's what recharges the batteries. We have an antenna that comes out the top that communicates with the rover. We don't communicate directly to Earth because they require much heavier equipment and we can't afford that extra mass. So we communicate just to the rover via radio. We have the fuselage, which has all the nuts and bolts, as well as thermal insulation, so we don't get too cold overnight because it gets down to negative 100 degrees. That will break a lot of electronics, and we don't want that to happen. We have the 4 legs that come out, super lightweight, but very strong carbon fiber. And the actual scientific payload, if you want to call it that, are 2 cameras. One is downward looking. It's this navigation camera, grayscale, 640 by 480, super fisheye, and that's just for navigating on the fly. The other is a bit more fun. It's a 13 megapixel color camera. And both these cameras were taken commercial off-the-shelf cameras that were used for cell phones. And they're lightweight, only about 1 gram each. And so that seemed to fit our purpose pretty well. And that's essentially the basic schematic of the helicopter and what we plan to do with it. For a little bit better understanding of the scale, here's what it actually looks like. This was in the, I believe this was in the vacuum simulator that we have when they were doing some of the testing and assembly for it. And there's some of the engineers in their cleaner equipment for that. So it's decent sized vehicle, pretty lightweight. And yeah, it's this is when it's in its fully deployed form. However, to get to Mars, you don't want to just stick it on something and throw it at the planet. There's a lot of issues going to Mars. The easiest way for us to do that was to ride with another vehicle. And so we ended up hitching a ride with the 2020 rover. And here's a picture of it, also in the clean room in the high bay. And what we ended up doing is we attached the helicopter, folded it up, we fold the legs up, made sure all the blades were locked together, kind of rotate it up on its side and just smushed it against the bottom of the rover itself. If the rover happened to have come down on a rock and landed on a rock, that would have been very bad. And well, thankfully it didn't happen, but there's always a risk of something going wrong. Because it's just a technology demonstration, we don't really have many mission requirements. So if something did happen to it, the rover is much more important. It's $2.5 billion. You don't want it to get hung up on something. And if needed, they could have just like detached the helicopter and just scraped it off as they drive away. But thankfully, that didn't happen. The other thing that we have to worry about is when we're landing, it can be a little bit messy. And when the rover is landing, it's got rocket jets from the sky crane that are blasting the surface, throwing rocks and pebbles and dust around. And you don't want a piece of that to come and damage the helicopter or the rover itself, for that matter. So there are a bunch of baffles and shields that were put into place to protect that. But despite the pandemic and all the challenges that presented, we were able to deliver the helicopter, the rover, get everything put together, and make our launch window when the orbits of Earth and Mars were in the proper configuration so that we could get an easy trajectory from one to the other. And so on July 30th of 2020, we indeed launched. So we went up on an Atlas V rocket with 4 boosters attached to it. This is from Kennedy Space Center in Florida. Launch was nominal, and yeah, Ingenuity and Perseverance were on their way to the red planet. The cruise itself took about 8 months to get there, but when it did, we used the 2020 rover's landing system with the sky crane, which slowly lowered the rover down onto the surface. Also, a fun thing is I'm the activity lead for these cameras, and it was incredible fun when these images came down. Being able to see us landing on Mars like this for the first time. But as you can see, it got a little bit messy when we landed. There's a lot of debris flying around through there. And the sky crane that had the rockets on it that lowered the rover down, it was 8 meters above the surface. It was a very violent interaction, and more so than we even expected. But thankfully, the helicopter was protected. And when you look underneath it, and this is an actual picture from Mars using the rover's arm that reached underneath and took a picture. Here's a picture of the shield, the protective pebble shield that was surrounding the helicopter and then dropped off once we were on the ground because we didn't need it anymore. So thankfully that protective shield helped to keep the helicopter safe and not dinged up by all these chunks of rock that were flying around. It did its job. You still see a little bit of sand in the bottom of it. It didn't form a complete seal, but it was enough that there were no big chunks flying around. And with Curiosity previously, some chunks even landed on top of the rover deck and damaged some of the weather instruments. So we wanted to be extra careful with this. So we drove away, dropped that pebble shield, and then the helicopter was exposed, curled up underneath, waiting to get deployed. Now, when we landed in Jezero, we had an 8.5 by 8 kilometer ellipse. We could have landed anywhere in the air, but typically you land towards the center, sort of a Gaussian distribution. And when we came in, we were trying to avoid any hazardous features. So the autonomous system took us to an area that I had personally previously mapped out, and it looked like there were no big rocks. There were no inescapable ripples. A couple small ones are fine, but as smooth, flat, and boring of a place as you could possibly imagine. And the system did what it was supposed to. It brought us down in at the location shown here, and there's a little bit of regolith, a lot of sand, a little bit of fairly smooth outcrop that you can just see poking up above the soil. But overall, a pretty benign place. We didn't land over on the left here where there's a ton of ripples, there's a bunch of big rocks. We thankfully avoided that. And from the helicopter perspective, when we landed, this is great. I mean, it's a nice, smooth, flat area, exactly the spot that you want to drop off and deploy the helicopter because, well, you don't want a really complicated terrain for a simple can it fly demonstration. So we ended up choosing the location here in that airfield. For scale, the line going from the bottom to the top, that's a notional 50-meter length flight that we were considering, and we ended up flying for flight 3. The inner box is where we actually deployed. That was a 3x3 meter area, basically the footprint of the rover. I want to make sure that there were no big rocks underneath there that would tilt the rover in such a way that it might cause problems during deployment. And then we had a broader 10 by 10 meter airfield that when we took off, we wanted to make sure we could actually land back in a safe area. So I wanted to make sure that was also free and clear of rocks. And then just a broader flight zone around that as extra cushion. As for what we see in the navigation cameras, we don't want anything to be odd and mess those up. So when we got there, we looked around. We needed to verify that, yes, it looks good from orbit, but that's only, tens of centimeters per pixel resolution at best. We want to make sure that it was really good on the ground because the helicopter is sensitive to rocks even as small as a few centimeters in height. So we used the rover's cameras, even from the first few days, first few sols on the Martian surface, to take panoramas, get them in stereo, and understand what the terrain was like. And here's a visualization of these images looking out over this airfield with that 3x3 meter deployment area right in the center there, that smaller green box. And it's pretty flat, smooth, and boring. Exactly the kind of thing we want for a really simple technology demonstration. And so after 40 some sols on the surface, we were able to verify that this was indeed what we wanted. We went down the airfield and imaged the entire way to make sure that the entire flight area that we wanted to fly over would be safe. And then we came back around and dropped off the helicopter. And hopefully this is playing. And then, yeah, the helicopter over a series of several sols slowly unfurled, releasing pyros, calling certain legs and others to make sure that everything was going ahead. So each one of these was a different day, a different plan that we had to go through to do that. And when we got to the end, when it was fully vertical and both legs deployed, you can see there's not a whole lot of space between the helicopter and the ground. And that's where our sort of few centimeters of clearance came in. The little fun thing we didn't expect is if you can see at the top, there's those sort of reddish or orangish cables. were sort of moving around. They ended up hanging down a little bit lower than we expected. So we had to take an extra couple days to make sure that the antenna on top of the helicopter wasn't going to get snagged on those cables and break, because, well, that would be bad. Then we can't communicate with the helicopter and do anything with it. Thankfully, we ended up having about 2 or 3 centimeters of clearance. That's about all we had, but it was enough that we could drive away safely. And then the last image there is us on the surface, safe and sound. The rover then drove off a little bit and decided to take a selfie. So here's the resulting mosaic from that selfie. It used the camera on its arm to do this, and by moving the camera around in such a way, the arm itself basically ended up being photoshopped out just by the way that the images were taken. Some had it in it, some didn't. I don't know why I'm getting that. I'm getting a very symbol on my screen. But yes, we were able to take the selfie of the rover with the helicopter right there while the helicopter is doing some of its internal checkouts. The first step after that was then to unlock the blades, and I have a video here showing that. So do one, then the other. We have these blades normally during flight rotate in opposite directions. Just to basically cancel out the angular momentum from the spinning blade, and then still providing a lot of downward force and lift. So thankfully, you're able to deploy these. This is probably one of the more strenuous days because it was one small latch for each blade, and if it didn't go, the entire mission was dead. Thankfully, it all worked. We then started to ramp things up and spin the blades, see what happens. And you can see in a couple of these different frames, we not only spin them around, we also adjust the pitch. And that's part of how we control the helicopter when it's in the air, by controlling the pitch, controlling the feathering, and making sure that that we have that full surface control so that we can control the helicopter, fly it around in the directions we want to, and not simply just go up and down, even though that still was the first step. And on April 19th, we did just that. We did our first flight up and down, 2 meters up, turn, 2 meters back down. And we went at about 1 meter per second speed doing that. So very quick and simple flight, but it worked. We could actually fly a vehicle on Mars in the air. And here's the plot from that. We took images with the navigation cameras looking down. Here's the more famous one of them. We're taking them constantly at I think it's like 30 FPS, but we're only saving out a few of them because we don't need all those images, and we have very limited downlink capability back to the rover and then from the rover back to Earth. But the helicopter wasn't the only thing taking pictures while we were there. We also had the rover itself, and it drove off to about 65 meters away, and then pointed its cameras at the helicopter. And the Mastcam Z instrument, which Jim Bell at ASU, he's the PI of, and he has a whole team working on it there. They recorded our flight in video. Hopefully this will now show. This is the first flight. Spin up the blades. Get up to high speed and take off. So we got up to the 2 meter altitude. Just hover there, make sure that we're stable. Give ourselves a turn, make sure that we can demonstrate we have motor control and surface control of the vehicle. Hover for a bit longer, make sure we're stable, steady. And then we slowly landed. And bloop, nice soft landing. Very unstressful for the vehicle. So then we can do future flights because, well, you don't want to have a vehicle that just flies once. You want to be able to use it over and over again. Now, it's a little bit hard to see in that video, especially with it probably compressed over Zoom. But in addition to just simply having a successful flight, we actually got some cool science out of that from the rover's perspective. this is a analysis done by Mark Lemon on the MassCamZ team. And on the left is showing a difference map frame by frame, and on the right is showing that added back into video. And you can see that we actually lifted up a bunch of dust when we took off. We were concerned that we might have a little bit of dust and, well, it could get on the solar panel. However, with the helicopter flying, the little bit of vibrations it had got all the dust off the solar panel, even some of the soil that had gotten on there during landing. But we were able to blow off an area on the ground where there was a bunch of dust previously, and it just gets taken away by the wind to the right. And this was actually before the wind sensors were working on the rover. So from the helicopter flight itself, we got our first estimate for the wind speed at this location on Mars, and it was 2 or 3 meters per second. So not too bad. We normally can fly in up to 8 meters per second. So flight 1, we did it. We actually flew. Then comes the more fun part. Okay, can we actually go somewhere and do something with it? Now, in order to do that, we need to be able to navigate while we're flying. And there's a few different ways that we were able to do that. On board the helicopter, we have an inertial measurement unit that tracks accelerations as we're moving. It has a drift effect though, so it's not super reliable. We want to balance that out with live active navigation using the navigation camera looking down. So in this case, and I will show the video on the right. Here we track features live on board the helicopter entirely autonomously, and reject certain outliers that don't seem to fit well. But this is helping us track how far we're moving over the surface. If you can combine this with the camera model, the laser rangefinder to get the altitude, you can then understand what your horizontal motion is, and then compare that back to the IMU, the inclinometers for the attitude, and then understand where you are with pretty good confidence in three-dimensional space live on Mars. Because we can't just joystick this around. We have to program the flight out entirely autonomously ahead of time. So it needs to be able to track itself in 3D space as it's going throughout its flight. And this is what it looks like from the helicopter's perspective. So on flight 3, we only did a 2 meter to the side and back. Flight 3, we did a bit farther. And we got a bunch of the images down from flight 3 as we're flying. And if you stack them one on top of each other and correlate them, you can then see the shadow of the helicopter flying over the surface. And from these images, we can start to build up more and more data and then actually start mapping what's underneath the helicopter as it's flying. So flight 3, which I'll show you the video of here, again, MassCamZ took this. Flight 2 is just 2 meters to and away from the camera, so that wasn't terribly exciting video-wise. But flight 3 is when we decided to fly 50 meters to the side at a 5-meter altitude. And there we go. So this is along that path I was showing earlier, 50 meters to the north, which is to the right. And we just keep going. So this entire flight, we went out 50 meters, and then on the way back started taking some pictures. This is real time. It's going to take a minute for the helicopter to come back because we flew a little bit farther than the cameras actually had a good field of view for. But it actually worked. It succeeded. We flew where we wanted to and back, just like Bilbo Baggins in The Hobbit, there and back again. You can see as we start approaching, we'll angle back to slow ourselves down, and then nice easy touchdown. And we nailed it. For the first 3 flights, we were within a couple of tens of centimeters accuracy of where we wanted to land. Very, very good control over the vehicle. Now, I mentioned as we flew out there on flight 3, we started taking pictures. And although these are technically in reverse order, I think it's easier to see from where we were closer up. So flight 2, we just spun around, taking some pictures. A bunch of rocks, some rover tracks. And then on flight 3, we started flying away. So I'll go through these a bit more slowly. So here, as a geologist, I'm seeing all these rocks lined up This is just really cool. It's telling you something about the structural geology. In this case, there's probably large fractures that are controlling this, and likely pervading with depth. In the sort of lighter area, that's where the sky crane blasted the surface when the rover was landing, scouring into it and actually exposing some rocks that were underneath the soil. And then the rover driving around multiple places after that as it was checking out some of its mobility systems and then ultimately deploying the helicopter. So started out, this is right over where we deployed the helicopter, flying a little bit farther away. A little bit farther still, you can still see the blast marks in the top of the screen. And then finally at the 50 meters distance, and we actually flew over some ripples here that are in the foreground right below us. Thankfully, a nice smooth area for us to fly over. One thing we were hoping for, but didn't exactly expect, was to take a picture of the rover from the helicopter as well. And we did that. It's up in the top left corner there. We actually got to take a look at Perseverance up there. So by the end of flight 3, we had accomplished all of our mission objectives. We demonstrated we can fly. We definitely demonstrated we could fly somewhere and back. We can do multiple landings. At that point, we were staying up in the air for about a minute. Ideally, we were the spacecraft was built to go 90 seconds, but start small, work your way up. And we were getting telemetry from the IMU, from the images to then help us reconstruct what happened during the flight and be able to work on future aerial vehicles in the future. So great, pre-flight's down. We'd already completed our mission. Now what? Now what can we do? Well, we've landed one place, and the rover had spent a lot of its resources making sure that we could land at our initial landing site, which we called Wright Brothers Field, because it's the first landing on or takeoff and landing on Mars. Well, we want to see if we can go somewhere else and land somewhere else, and that's what we attempted to do on flight 4. So flight 4, as I'm showing here on the left in map view and on the right as the images from the helicopter as it saw it while it was flying. We flew down towards the southeast to areas that looked like they might be smooth and flat and boring, safe for landing. And the images all you see on the right, those were all processed and mosaic together to show the gray image on the bottom, in the left image on the bottom of it. So we can map those out on the surface, tie those into images from orbit, and then correlate them to understand exactly where they are in three-dimensional space. And by looking at the images themselves, we can get a much higher resolution on the order of only a few centimeters as opposed to tens of centimeters to see if there are any hazardous rocks, slopes, ripples, anything that might prove a hazard for the helicopter. So as you can see right there, there's a little bit of a bump on the right side. That was a ripple, and we didn't want to land on that. So we knew where not to go. And so we ended up for flight 5, which is the next slide, flying down there again, taking color pictures. And this is towards that area at the bottom. Nice, smooth, open area, fairly sandy surface, no big rocks sticking up that we'd get tripped up on or would accidentally hit the fuselage of the helicopter. Just got to watch out for that one little ripple there. And as we got closer, here is where it was right over it. Yeah, we didn't want to go quite that far. So we ended up landing just short of that. So flight 4, we flew there and back, doing a scouting run because the rover hadn't taken pictures of that area. We did our own scouting. And then flight 5, we actually flew down there. So yeah, this image was from flight 4. You can see we're still moderate distance from the ground. This is 5 meters altitude. In flight 5, we ended up flying up to 10 meters. So that ripple, you can see sort of bottom, a little bit left to center of the screen here. That was the one that's sort of bottom and right of screen here. It's a bit higher up here. You still see everything pretty well. And we ended up landing directly below this at the very bottom of the screen. And this is the last time that the rover took pictures and video of the helicopter. After that, we started looking a little bit farther. But so far at that point, within just the first month, we had done 5 successful takeoffs, flights and landings, and we were ready for more. At that stage, we transitioned from a technology demonstration, simply just can we fly, to what can we do that's actually scientifically valuable and can benefit the rover itself in a manner that isn't going to be impeding its own capabilities. We don't want to have to have the rover take pictures of every new site we want to go to. We want to see if the helicopter can do that on its own, so it's not a burden on the rover or its own science. So taking a broader perspective, sort of on the orbital scale, looking down, here's what the rover has been generally planning for the past 6 and 7 months, and then looking beyond as well. So we landed in here at the top, turn the right side, at the Octavia E. Butler landing site. That's where the rover was at the time that we finished our 5th flight. And the helicopter was at Blue Dot. The rover was a little bit farther north in where the white line is. And the rover wanted to go down and around to some cool rocks in the sea to south region. Unfortunately, that rough looking area in the middle of this region is exactly that. It is rough. There's a lot of rocks. They're rather large, and there are a bunch of sand ripples that go throughout it as well. And so trying to navigate across that region itself would just be an incredible maze and extremely difficult to navigate through. So the rover would have to go all the way around and couldn't really even drive into it directly until you got to the smoother area by C to S that at least looked like it was smoother from orbit. So, well, we want to have the helicopter useful. Let's see if we can go and scout ahead, see what might be over there. And so flight 6, we started doing that. We started going and looking towards that C2 region, and it's at the very top of the image here. However, when we started flying closer towards it, stuff literally started going sideways. This was not expected and was a major anomaly that nearly killed the helicopter. We started oscillating rather violently because the image buffers were getting full. And we were taking these color pictures, 13 megapixels, a lot of data, as well as the navigation camera images constantly at 30 FPS. And with the frequency that we were starting to take the color pictures, that ended up exceeding the buffer of the navigation camera, and one frame from the navigation camera was missed. As a result, that increased a time delay in the timestamps of all the subsequent images. So when we were trying to track features, we were tracking features that had already moved, and we thought it was a point in the past, or we thought it was a point more near in the past than it actually was. And so as a result, this happened. And this is approximate true time. We were going quite a bit off axis, and the helicopter was really struggling to maintain stability. And somehow we still landed within 6 meters of our target after about 100 or about 230 meters of flight. But if we had lost a second navigation camera frame, a second image from navigation camera, we probably would have crashed and it would have been over. So we learned something. Don't just keep assigning them sequentially. You need to make sure that you're actually checking back to make sure that it's the right image. And eventually a fix was applied to that, and we could continue flying. But for the following 2 flights, we couldn't take any color pictures at all. We just started hopping, doing short hops with only the navigation camera about 100 meters at a time towards the south, just to keep up with the rover. Now, eventually, when we got a little bit farther south, we got that fix implemented on board the helicopter. And well, at that point, the helicopter and rover were both where this orange dot were. And rover had to go all the way around, but the helicopter, it could fly over these hazards. It doesn't have to worry about what the rover's driving over. So that's exactly what we did. We cut the corner and flew across this region that the rover physically is not capable of driving over. So previously we have been doing 100, 200 meter flights The largest was 270 meters, which was itself a record for autonomous single day traverse on another planet. Flight 9, that was 620 meters and went for 2 minutes and 46 seconds versus what we thought we would originally be able to fly for was only 90 seconds. So this was a full minute and 16 seconds longer than we thought we were actually able to do. Weren't sure this was going to survive. We ended up picking a huge area from entirely orbital pictures without even flying the helicopter ahead to find things. Verified it as we thought it'd be safe. And sure enough, the helicopter actually flew across successfully, despite the terrain over the area that we were flying over. And just for another scale, this is not only an issue just horizontally, but vertically, where we took off and where we landed, we're about 16 meters of relief distance, like vertical distance. So it's a huge change in topography over that. And when the helicopter's flying, it assumes everything's a flat plane. So the fact that this actually worked is kind of phenomenal. It just really speaks towards the engineers who designed and built this, that it indeed was able to handle that. The navigation movie, the full thing is on the website, but I'm going to start moving towards a couple of the other color pictures because we got color pictures across this entire thing. So the rover had just driven away from us because we didn't want to get too close to the rover when we were flying. And so here are a couple of its tracks right as we're about to depart. And you can see the CETA region with its hazardous terrain up towards the top. We're going to start flying over these ripples. The rover can't drive over because it's sand, just can't get good traction. But helicopter can fly right over. And we did. But in addition to that, you can also see that there are patches of these rocks that are scientifically interesting, but the rover just can't actually access itself. So helicopter keeps moving. Here in this case, you can see some layers in the rocks, or what looked to me like layers in the rocks on the right side. That's something that the rover hadn't been able to see it because it couldn't go here. So we were able to do this reconnaissance from up high. Getting towards the other side, started to smooth out a little bit more benign. See here that there are some large fractures that we could kind of see in the earlier images, but in this region, they're showing up bright as daylight. And then the other side, we start getting more rocks. This is the other edge of that CETA region. And beyond which, we start finding the flatter, smoother, safer areas to land. And here's the last image from that Flight 9 that was taken. We ended up landing on the left side, just about here. But we had this huge area that we had thought from orbit looked good to land in. And indeed, it was very safe to do so. So Flight 9 succeeded. Yeah, the previous record for a single day autonomous traverse or distance traveled on another planet was by the Opportunity rover at 228 meters. And yeah, 620 kind of blew it out of the water. And even Perseverance is never going to be able to reach that mark. So for the foreseeable future, Ingenuity is going to hold that single day distance record. So, okay, we made it. We made it across this huge challenging terrain. Now what? Well, there's some cool rocks in the distance out there. And the science team said, let's take a look at them. So when we look at it from orbit, and this is what the orbital view looks like there is a series of these really big fractures, except these ones have rocks and dual ridges sticking up on either side of them. And it appears that they actually come to a triple point. The rover at this point was still 400 to 500 meters away, half a kilometer, and it couldn't even see the helicopter at this stage, never mind the rocks around it. So we decided to take the helicopter for a spin and do some reconnaissance. And here's what that looks like. Here's that triple junction where these ridges and fractures or parent fractures are coming together at a triple point. There's people working on papers on this at the most. I can't say too much about it, but this the structures here that we're seeing, the angles involved, the rocks that we're seeing, this is indicative of the sort of environment that was present billions of years ago. And the rover has never gone over here. So this is entirely going to be based on helicopter data that we're able to make these assessments, unless the rover decides to drive there in the future. So we can actually see this cool science from where we are with the helicopter. And here's another view looking a bit more off to the side of one of these fractures veering off to the right and into the distance with the rocks on either side. So we were able to perform that. In that case, we had, I think it was 10 distinct waypoints. So that was the most complicated flight. It wasn't just going from one spot to another. We had a bunch of different spots in between with rotations at each location. And that's what you see at the bottom here between these two green dots. It was a fairly complicated pattern. So, okay, what more can we do? Well, the rover wanted to get up here to the South Seti area. And that was a bit of a challenge for it to get to, but that was only a single flight away for us. So flight 11, we did fly up there, and then flight 12 and 13, we started looking at it. And that's where we are now today. So at the end of flight 11, here's where we ended up. Nice, smooth, sandy spot, just like we thought it would be from orbit. We've landed 3 times within this field of view now. And then flight 12, we decided to go venturing off into Sita and look at the area that the rover was still several hundred meters away from us, but they thought that we wanted to go into that region to look at the rocks because it looks like it's a different geologic unit. It might be older than the rest of the rocks that the rover had been driving over so far. So trying to understand what those rocks are and what we can access with the rover potentially was really, really important for the team. So we did just that. We flew over there, flew over that ridge, flew over these ripples, big ripples, and started getting to some of these cool rocks in the middle that in this image on the right side, you can see even have layers. So more of these layered rocks, which generally indicate some sort of either depositional process, because this is an ancient lake environment, could be layers of rocks from that, or maybe from some sort of weathering event, from fractures, different maybe volcanic lava flows or ashfall deposits. There are a whole bunch of hypotheses that we still need to test. And right now, the rover has finally gotten to this location just in the past few days, and it would be just off to the right of where this field of view is. But we're currently parked right there and will be for the next probably month as Mars goes behind the sun from our perspective. The helicopter was able to fly over here and basically show where it was safe for the rover to drive to access this location. So that was flight 12. And then we flew back to that same spot. Flight 13, there was one other little outcrop off to the side that looks really cool from orbit. You see a bunch of rocks, but it's a few pixels. You can't make much of it. So we decided to go look at that. So we decided to fly out there. In this case, we're looking west back at where we landed before, which is at the top of the screen here. And I'm going to move through these next few pictures in sequence. So we took pictures along this ridge to get stereo perspectives and be able to rebuild digital topography from them. And that work is still ongoing, so I can't share that information yet. But the images themselves, I think, are quite telling. You see here already that there's layers being exposed. And as it flew along this ridge and outcrop, you just see the layers really starting to pop out. And because this rover team is actually considering going over to this outcrop, which it previously hadn't been considering doing, this may be directly influencing and contributing to the science goals of the mission, because this is the clearest signs of layers we've seen yet along where the rover is. We've seen them in the distance, but this is the first time we've seen them potentially really up close. So the helicopter may have, through its flights, is directly contributing to the science planning for this. And I don't think we're going to get here before Mars goes behind the sun for conjunction, but once it comes back out the other side, when we can regain communication, my guess is we'll probably end up going over here and with the rover in a future set of drives. And we might even sample this rock, TBD. But this sort of layering is just, it's really cool, because this is indicating some sort of process was going on to create these layers back 3.5 billion years ago. And we're now able to see and identify locations and say, this is where we should be looking to make these observations. So after the helicopter did this survey, this sort of walkabout of an outcrop, it then flew back to its landing site, which is again at the top of this picture. And that's where we are now. So flight 14, and we also just did do another test. So what's coming up next is flight 14 is in the books. It has been planned, and plans have been sent, or at least last I checked, they were being sent to Mars. We should hear back about that very soon. So I recommend, if you're interested, probably in the next day or two, to check the JPL Twitter account, because they post updates on that as soon as we get the information back, whether or not a flight succeeds. So hopefully we'll be able to see that there's another flight then. This one's going to be a little bit simpler. We just did a high-speed spin test up to 2800 RPM because the seasons are changing. We want to be able to keep flying. So with atmospheric pressure dropping, we need to spin the blades faster, make sure the helicopter can actually spin its blades faster. So we did that test on the ground, and flight 14 is going to do that test in the air and only shift probably about 2 meters off to the side. But we'll still be able to do that and demonstrate that we can continue flying as the Martian year progresses. And hopefully we'll be able to continue flying until I've been hearing estimates being thrown around of March or potentially longer. We've been able to do so much with this mission so far. We're not really sure how far we're going to go. Any one accident and it's all over, especially with the blade spinning that fast. If one of them hits the ground, it is done. But so far, it's just been phenomenal, and we're wondering how far we can really push it and what maximum science we can really get out of the helicopter, even if it was just originally a tech demo. So it's a really quick summary of what we've done so far. We have flown almost 2.9 kilometers, 1.8 miles total so far. Bit more than what we were planning originally. Our baseline was only 100 meters out and back. We've blown that away. 13 flights now. We originally planned up to 5 if they actually worked at all. We've now survived for, it's currently Sol 206, and we've been on the surface that entire time. So it's just been, the spacecraft is still perfectly healthy. There's no signs of mechanical wear that we've been able to see so far. We've flown almost 25 minutes at this point, cumulative time in the air. And yeah, originally we thought we'd only be able to fly 90 seconds at a time. We've gotten up to 2 minutes and 46 seconds and still had margin on top of that. So it's just a phenomenally capable vehicle beyond our wildest dreams and hopes. I had to list a couple of the stats here of just what we've been able to do. Some of these I mentioned already. We've taken almost 1,600 navigation camera images that we have downlinked, that we've actually sent back to Earth. There's been a ton of other on board the helicopter that we just don't save, that just go into the navigation filter, we track, and then throw out. But some we do save. We've downloaded almost 1,600 of those, and 82 of the color camera images. And those are all available. If you want to look at every single one of them, you can do that on the mars.nasa.gov website. There's a raw image page for all the images for Perseverance and Ingenuity, and you can filter them, you can look through them, and enjoy them to your heart's content. Those ones they tend to be more the raw images. The ones I've been showing, I just did a quick color correction for them and vignette removal, so they look a little bit nicer. But all those images are up there, and the process versions will be released to the PDS, the planetary data system, at a 6-month cadence. And I believe the first set is already up there from the first 3 months of the mission. So far, we've flown up to 12 meters in altitude, 39 feet, up to 5 meters per second ground speed. And we've also flown into the wind at 5 meters a second with a 5 meter per second approximately wind as well. And the helicopter has been behaving fine. We fixed a couple issues with the anomalies, and even throughout those anomalies, the helicopter performed as expected and really doesn't have any signs of mechanical wear. So we're thrilled to continue flying. And even as the atmospheric pressure drops, well, we'll keep spinning a little bit faster and faster and see what more boundaries we can push. So now for the journey ahead over the next, who knows how long we'll be able to keep going. We're gonna probably start going back around the CT unit because the rover still doesn't want to drive across it. It's incredibly hazardous. So the helicopter will probably either follow behind or try to fly ahead of the rover. Sort of backtrack going counterclockwise around here, back up by the original landing site, and then going all the way around over to the Three Forks area, right at the base of the delta, where you can see there's a bunch of layered rocks that await us. And who knows what the helicopter will be able to do further. It's just phenomenal to be able to get this far. And I'd like to thank the team, the helicopter team, thank all you guys for listening, thank the rover team for its support throughout all this. And I will leave you with just all the pictures that we have taken, all the color pictures we've taken so far, and happy to answer any questions that I can that aren't being, aren't technology or access restricted.
Thank you, Nathan. For the people in the Q&A, or everybody, please put your questions in the Q&A, and I will attempt to enable your microphone so you can ask it live, unless you don't have a microphone or tell me you don't want to ask it live. Before we get to that, though, so Nathan, some of our, I think we have some undergrads and grads in the audience. Could you describe what like a typical day at work would be? If there's anything typical, or what decisions do you have to make, or what, because I mean, when I first graduated, I had no idea what a typical day at work was going to be, which is completely ridiculous. So if you could shine any light on that, that could help future people awaiting that first day at work.
Yeah. Yeah, the last 6-7 months have not been typical. I'll start with that. But at the same time, that's been phenomenal. I'll talk about what that's been like briefly too. Normally, pre-pandemic, before times, I would go into lab, have normal work hours, whatnot. And originally I started off in the science division at JPL, more focused on hypothesis testing, but I was also working on the maps for the rover to land with, and choosing where the rover would go. So that was a lot of working with both scientists, with engineers, trying to communicate between the different groups to make sure that everybody was on the same page, everybody understood what they needed, what they had, and what they were going to be applying to the mission to make sure it worked, and then verifying everything. So it was a lot of communication. I think that was really the biggest skill test that I had when I started, was being able to communicate as almost a liaison between groups that normally don't talk to each other that much. Scientists and engineers often have a very different language in how they speak. And so being able to translate and communicate between those is really key, because you need to be able to understand both the requirements from the science side, what they really need to get out of it, and then what they know about the environment that you're going to be in. And then there's engineers who they have their mechanical, their logistical knowledge and understanding. They have their requirements for what vehicles simply can do, but they don't always know necessarily what they need to be using it for, and what the environment is in that it's going to be at. So being able to merge those two worlds together, for me, has been the greatest challenge, but also the greatest reward in the work that I've done. And it's been a fairly standard thing in terms of other work stuff. Just for me, it was a normal work day, sort of 9 to 5 kind of thing. Just, I go on lab, and, they're building the rover right next door to where I work. So it's kind of crazy for that. When we landed, though, everything got turned on its head, because we were working on Mars time for 2 months. And that was 24 hours and 40 minutes a day. Yeah, some days I wake up at normal times. Granted, this was all in the pandemic, so I was working entirely from home, as I still am. But dialing in on, not Zoom, but we have another video conference, and throughout the day, just doing a shift. However, because the day-night cycle on Mars is a little bit longer than ours, it shifts over time. So I'd start in the morning sometimes, and then it would get later and later and later. And soon I was waking up at 10 p.m. and working throughout the night and going to bed at like noon. It's basically like perpetual jet lag.
Oh.
It's kind of insane. if there's a time to do Mars time, it was probably during the pandemic, because it's like I didn't need to go to the bank or anything because the banks weren't going to be open. And supermarket stuff, I just have to organize delivering my food, because otherwise I was basically locked inside working on this for 10 to 14 hours a day, and trying to get some sleep on top of that. But it was phenomenal to be able to do that, to be working constantly on that. After those 2 months, other people in the team were really burnt out. I think I held it decently well, but burnout slowly gotten up to me. But now we're only doing we're doing 7 day a week operations, but now it's instead of being 24 Earth hours a day or 24 40 for Mars, it's now we're only having shifts from 5 a.m. until 11 p.m. So huge improvement. Don't have to do any more 2-3 a.m. rover shifts. And then starting October, I actually have Sundays off.
Oh, that sounds good. So like, to pick a path, would you propose a path, or would you pull the various teams together and they would have a discussion as to what each team wanted the next flight to be, and then they come to agreement as to what it is, or how would that work?
Yeah, it's a little bit challenging and complicated. There's a lot of politics involved, and especially very high level management saying we want to do this and that. So in terms of some of that, I've been doing a lot of the more ground level mapping of here's where we are, here's where we can get to. The actual decisions have mostly been coming from the science team. We are sort of serving on their behest. And so the helicopter team has been basically just saying, okay, science team wants to go this area, let's see what we can do to make that happen. And so in that case, it's been a lot of back and forth of here's what we can do, here's what we can't, here's what's in their capabilities, here's where we might be able to get pictures to optimize this, and then talking back and forth with the science management to get everybody on the same page and agree on that. Originally, it was entirely myself, my former postdoc supervisor, Matt Gollenbeck, and the helicopter chief pilot, Hovard Grip. It was the three of us that were originally planning that first spot. We had a couple other helpers along the way, but we were the leads of that. So that first 50-meter out and back flight was just the three of us. And that was just, talking to the teams, making sure everybody knows what we can do, and just trying to find the best thing that we can within the geology and the terrain that we are given.
Okay. Let's see, I'll move to the questions. David, your mic is live if you'd like to ask your question in person. Are you still there, David?
Try to see if I can bring up chat as well so I can see.
Okay, got it.
There we go.
What are the parameters of Ingenuity insofar as max distance, max speed, still within control, but what is that thing actually capable of?
So we have blown by our expectations. So it's at least 620 meters max distance. Our top speed so far that we've achieved and performed was 5 meters per second, and I believe we did that on 3 different flights, all successfully. I think we could potentially go faster. The challenge with that is when we start flying faster, if we're close to the ground, then the features that we're trying to track with the navigation camera, they're zooming through the frame and we lose them. And then that increases the uncertainty. And once we have less uncertainty, we may not land in the spot that we want to, and that could be very bad. So right now, that seems to be the main limit is how quickly things are moving through the field of view. We can ameliorate that a bit by flying higher. And right now, the maximum altitude that we can fly is, well, sort of 15 meters. However, that's a soft limit. It's only 15 meters right now because it's been coded into the hardware or into the software for the hardware to respond to that if the altimeter says we're at over 15 meters in altitude, it's just going to assume that those are bad readings because we weren't originally supposed to be flying that high. So in a future update, we will probably remove or at least limit that constraint for some flights and be able to fly higher and then be able to fly faster. In theory, we don't know what the upper bound is for that. For distance, we have thought about potentially flying at 5 meters per second for maybe even up to 1 kilometer. We don't know. We were originally thinking that sort of 200 meters would be the best that we could do, and we've just blown by it. Same with the duration. We originally thought we'd be pushing it at 90 seconds, minute and a half, and we've done 2 minutes 46 seconds. We did another flight for like 2 minutes and 43 seconds, and batteries have all been behaving perfectly. It's all been nominal. We still have margin that we can use, and we can push farther and harder. So we don't know yet.
You do have more capability on the battery to go further.
Yep.
But not using it yet.
Yep. We don't want to accidentally run into a problem, and we could make emergency landings. We do have that capability, but at this point, we haven't used that quite yet. As we start going back around, sort of backtracking, we may wish to do some longer flights to make sure that we can stay ahead of the rover. The rover now has auto nav capabilities that are working, and it's able to travel. I think its farthest it's been able to get so far is 275 meters in one sol. Typically, we've been only flying the helicopter every week or two. So if the rover can keep up those distances every single day, then we're going to have to start going farther and farther with each flight in order to keep up with them, or increase the frequency, which we can also do.
Okay.
Thank you.
So yeah, just to translate, 5 meters per second is about 12 miles per hour, I believe.
Yeah.
So if we're more familiar with MPHs.
Yeah. And the other one, which else is happening in my head, the strongest wind gust that we have flown against, like flown into, with a 5 meter per second ground velocity, was a 20 mile per hour wind, headwind. And helicopter didn't even show signs of slowing down. It still just pushed through. So there's definitely more capability there that the helicopter hasn't utilized yet.
Nice. And if you fly at 15 meters elevation, do you not kick up dust then?
Kick up less. We're not kicking up that much dust at all, and we really like Mark, when he made those images, he really had to stretch the heck out of them in order for it to show up. And when we're flying, the vibrations on the helicopter, it's vibrating all the dust and sand off. Between when we dropped off the helicopter and the end of its first flight, the power actually increased by something like 13% because we had jiggled off so much sand and dust. And we didn't have to take off for that sort of effect to happen.
Yeah,
so,
I was just wondering if it like obscured your pictures of the ground you're taking because you're kicking up dust.
we do occasionally get like a speck of dust that lands on the camera lens.
Okay.
And there is one right now. It's kind of frustrating, like trying to figure out like where we landed in. I'm trying to find this round feature on the ground. Oh no, that's a speck of dust, not a crater. But in terms of actually seeing the ground, it's so transparent. There's so little dust. It's not affecting us.
Okay.
And what few outliers we do get, the nav algorithm is able to pick out the outliers and say, no, it's not a real point, just ignore it, and track the real ground features that we're trying to match and model.
Okay. Let's see. Stuart had a question, but I don't think he's online anymore. He's just wondering about the life expectancy of the awesome aircraft.
As long as we can fly it.
Okay.
In theory, it could be March. That's the month I've had thrown around, but we don't know. We have pushed the boundaries so far, so incredibly. We don't know. It's whenever we have our first accident.
Oh. Okay. Jackie has a question.
Yeah, so that's a really alarmingly fast RPM speed on the rotors there. Were you able to test that at all at, Martian type air pressures, maybe in one of the big vacuum chambers that NASA has, or?
Yep, yeah, we have one at JPL. It's I think a 25-foot simulator. We were able to test it somewhat, but only sort of up and down and over a meter or two. That's just as big as the simulator is. So we weren't able to test out the full distance flights like the Flight 3 or even longer. But for the simple up and down, we were. So you could crank down the pressure on that, get it to more Mars atmosphere-like pressures. We never tested up to 2,800 RPM even on the ground though. We only did to the nominal sort of 2,500 RPM speeds in our test facility. The other thing that we did is because if you were to try that on Earth, not much would happen because of Earth gravity. So what the team ended up doing was they attached the helicopter to a spring to impart another acceleration. And then we were able to more closely simulate it. But even then it was only sort of up and down, sort of side to side. And it did wobble quite a bit. And it's actually on Mars so far been able to perform more stably than in the test simulator. At one point, it almost went off into the side of the building. And on Mars, we haven't had anything like that. We've been within sort of like 25, 30 centimeters precision in station keeping on Mars. It's been incredible.
Okay, good, Jackie. Let's see, James has
Yes.
it.
Thanks.
Okay, thank you. Go ahead, James.
Sure. I think you answered the question already. I was just, I gathered a lot of the problems with the stuff on Mars is that the batteries run down because of the dust gets on the solar things, but it sounds like not. So I was recommending why not put it on the blades and clean it off, but it sounds like there's so much vibration. That's not going to be a limiting factor on this instrument, it sounds like. So
Nope.
That's great. Okay. That
Yeah.
answers my question. Thank you.
Yeah. The other thing I'll mention just quickly is that the Perseverance is also nuclear powered. It's got a radioisotope thermoelectric generator, so it doesn't have to worry about solar power for its stuff like Spirit and Opportunity used to. Jezero crater itself, where the rover and helicopter are, it's also a very windy environment. We've been seeing dust devils all over the place and even getting videos of them. I think it was during flight 4 or 5. I'm not sure if that video is fully published yet, but there are dust devils in the video with the helicopter in the foreground. It's kind of phenomenal how windy it is. So even if there was dust accumulating, it seems to be getting blown around quite a bit. So not really a concern for us.
Thank you.
So yeah, Tom Curry doesn't have a microphone, and his question is, what provision is there in the design, speaking of dust storms, to prevent dust storms from tipping the craft over?
It can tip it, but because we have the inclinometers on board, it's able to respond very quickly to that. And because we've been seeing gusts upwards of 20 miles an hour, so far it's been able to handle those just fine. The other fortunate thing is that because Mars' atmosphere is so thin and tenuous, there's just not a lot of mass. So the actual force imparted on the helicopter is relatively small, even if the velocity of the wind is rather large.
Yeah, no Martian movie spacecraft.
No giant dust storms or haboobs like you get in the valley.
Yeah, all right, thanks. Henry, yeah, you have a question?
Yeah, hi. Excuse me. I'm just curious as to whether the blades have a different design on them versus, say, a similar type of vehicle for on Earth due to the different conditions and so forth. Is there a different design in the blades for Mars?
In terms of shape, not really. The blades themselves are carbon fiber and with a foam interior. So they're incredibly lightweight. You pick it up and it's like you're hardly holding anything at all, and you really just push the air around when you hold them. So I think the blades on Earth they're a lot heavier, they're a lot sturdier, but on Mars they just don't need to be because you don't have as much atmosphere that you're trying to push the blade through.
How about the airfoil design, though?
Design, it's chunkier. So normally the helicopter blades aren't nearly so broad or so deep, but it's general just airfoil design.
Okay, thank you.
Not very different. Yeah, if I can bring up the picture of that just to show quickly again. I need to show. that on top. There we go. Yeah, so the general shape is, I think it's a standard airfoil shape. And we just adjust the pitch of it as needed.
Thank you. Great talk.
Thanks.
Great work.
It's great fun.
Taylor.
Hi, just excited for the great work you did. That was really awesome. Has there been anything you've hoped or envisioned to do that as you went to plan it, that's not going to work and you had to scrap that idea?
Well, originally flying to the other side of CETO was originally scrapped because like, no, there's no way we can do that. And then we did it. We came back, we visited about 2 months after and actually flew it. So in that case, we did go through that whole process. In terms of for what we are thinking of for the or other things we haven't done, one thing we were considering, and this has been publicly talked about, so I can actually talk about it, is bring up the right slide. Is in this area, the rover is planning to go over here. Originally, it was also considering going down here to an area called Pilot Pinnacle. It's a large hill, I think probably 100 meters high or so. And it looks like it has some layers in it. So we were considering flying over there, potentially a couple kilometers ahead of the rover and scouting that out before the rover got there. We ended up deciding that, okay, the science and the rocks closer to where we are were of higher priority. We could potentially still fly over there after conjunction and take a look at it. But so far that has not come to fruition. And we may end up just starting back around going the other direction. But yeah, we considered flying off in that direction too. When we deployed, or when we were preparing to deploy, we were also considering other airfields in place of the one just right next to where we landed. We were considering a bunch of other ones that were sort of towards the northeast up here, but we ended up not needing to use those so far. However, if the rover starts going back up that way and we start following, we may end up using those as well. But so far, none of the helicopter's capabilities have actually proven to be an obstacle for getting to do what we've wanted to do. We pushed the limits with some of these flights, but we've actually succeeded. And now it's a question of what more can we really do? Are we really thinking big enough within the reasonable tolerances?
Nathan, while you have this diagram up there, what's the distance from Three Forks to say Ridges approximately?
So that's probably about 1 3/4 kilometers as the Martian crow flies.
Okay.
Yeah, and there is a scale bar. I thought I had a scale bar. There's a scale bar down here. So yeah, white bar is 200. The white and black themselves together are 400 meters.
Okay. Thank you. I didn't see that.
Yeah, I think it's about 1 3/4 kilometers. Maybe it's a little bit closer to 2.
Okay. Moving on to Jeffrey. Oh, he doesn't have a microphone. Sorry. Is there a possibility the helicopter could go out of radio range of the rover?
Yes, that was one of our earlier concerns as well. And we were thinking we might only have about 300-meter range, maybe even 250-meter range for the helicopter. I think the farthest away we've been now is something like 700 meters, maybe 750. And we still had the high data rate capabilities at that distance, even without line of sight. So who knows? In theory, we might run out of a signal when we start approaching like 2.5 kilometer range with line of sight. But even that is now thrown into question. And we've even started considering potentially having a basic flight every couple of days where we just hop up above whatever topography might be blocking the view, talking to the rover live for a minute or so, and then dropping back down. So at that point, the rover could send the helicopter new commands, even if there's a giant mountain in front of it. Yeah, we don't know the range, the full range. It's longer than we've been able to do so far.
That's a good answer. Jackie, go ahead.
Yeah, I was pretty surprised that you could just use off-the-shelf cell phone type cameras and they're space rated and they can withstand Martian temperatures, especially since you did mention that the electronics are potentially sensitive to the extreme cold. These really aren't special cameras in any way. Can I take my cell phone to Mars?
These are literally commercial off-the-shelf cameras. They are not intentionally space hardened. We also have the processor on board. It's a Snapdragon, like one you can buy from the store. Same with the base station on board, the rover that does the communications and additional image processing. It also has a Snapdragon and actually has more processing power than the entire rest of the rover combined. So if it keeps working and the helicopter for some reason doesn't, we might actually end up using the base station's processor for rover operations too. It's potentially susceptible to radiation. We haven't had any issues with it yet. There was a coronal mass ejection on Sol 150-ish that went by Mars, and helicopter's doing fine. We also have the EDL cameras, which are also commercial off-the-shelf cameras. We considered GoPros for those, but ended up not using GoPros. We used a different sort of camera, and we have a microphone for those too. The ones that are still attached to the rover and not crashed with the sky crane, the ones that are still there, also commercial off the shelf, also survived, and we're still using those. So apparently some of the stuff is still working. It may not be able to work for, the multiple years that other rover systems are, but so far, so good.
Okay, wow. I'll take my cell phone to Mars then.
You may not be able to rely on it, but so far, so good.
Oh, sorry. Sarah, go ahead. You've got a question.
Sure, thanks. And sorry if I maybe missed this, but so what all I guess goes into kind of verifying what sites and or tasks that Ingenuity can do, especially given, I mean, you guys have pushed a lot of boundaries, but you also still don't know where those boundaries are. So are there models that you guys run before verifying that this is the schedule that you want to send to the helicopter? And then is there other prioritization that goes into saying, okay, no, this is the thing that we want to do above everything else?
Yeah, so for the landing sites, that's now done entirely based on orbital images. And that's literally me looking at the orbital images and saying, here's a safe spot with a given expected radius or diameter for the uncertainty based on the duration of flight, the topography that we're flying over, and we do a Monte Carlo simulation for that. We have a GitHub repo where we have all of our code stored, and we run a bunch of MATLAB scripts. There's a specific program we use called Helicat. I don't know if that's actually publicly available yet, but it's been at least talked about publicly. And it's a simulation tool, so we just run it a bunch of times with different variables and see how it performs. And based on the dispersion in those models, we can then get uncertainty for where we think we can go, or at least land safely. But beyond that, yeah, it's performed within our and beyond our expectations every single time. And even with Flight 6, it was really struggling. It still managed to land within 6 meters of our target, and our predicted error within even with a nominal flight was only 5 meters. And we still did 6 with this major anomaly. So I think perhaps we're a little bit over conservative in our modeling assumptions, but if it works, it works. We'll keep pushing it.
Very cool. Thank you so much.
Okay, do any of our panelists have a question that they'd like to ask? Wayne, Gordon, Tom?
No, not from here. I think he's covered everything.
I'll throw you one more question, Nathan.
Go for it.
When Mars is behind the sun, how much of a, so what do you do? Do you hibernate, or how long is that period also?
So I personally will hopefully sleep. That's one thing I'm looking forward to. So it's the conjunction period is typically about 2 weeks where we sort of don't have any contact. We'll be listening still, but we get all of our communications from the helicopter through the rover, and from the rover through the relay satellites. So Mars Reconnaissance Orbiter, MAVEN, Trace Gas Orbiter, and Odyssey. We use all of those. We also have direct-to-Earth communications as well. But we actually just finished up the conjunction planning for the rover and helicopter. We're going to do a couple of communication check-ins over the conjunction. So just a pre-scripted series of events that happens for basically 2 weeks. And a few days before, we will just stop sending commands. We'll only listen because we don't want to send a command and have it get corrupted. That would be bad. And then a few days after, we'll just start receiving data and not sending any commands yet, just to start getting the backlog of data that we're collecting over conjunction with all sorts of imaging. We're doing new microphone recordings over conjunction as well. One thing I forgot to mention, if you want to hear what the helicopter sounds like, I wasn't able to get it hooked in here, but on the NASA website, there is actual microphone recording of the helicopter. It's a very deep buzz, but you can actually hear it too. So yeah, we're planning the stuff for conjunction. It's about 2 weeks, and pretty much all the team is going to be taking a break because it's been a long 6-7 months since then.
Awesome, thank you. Yeah, great talk, Nathan. Thank you so much for presenting to us today.
Thanks for having me. A couple of things I'll mention is JPL does, at least in non-pandemic times, and we probably will at some point in the future, we do have an open house day every year, usually in April. This past couple of years we didn't because of the pandemic, but hopefully we'll have that again. And for any undergrads who are out there, JPL, NASA also do internships as well. So if you're interested in doing this sort of work, either on the science side, engineering side, there are many opportunities available for that as well, for sort of summer programs if you want to see what it's like to work at JPL or in a sort of similar industry.
All right, thanks, Nathan. Back to you, Gordon.
Yeah, let's see. Can you hear me okay?
Yep.
Okay, great. Nathan, thank you for that excellent presentation. Wow, what a subject matter. This is something that we normally don't get a presentation on, something we normally don't see. So this was really exciting. Thank you so much for giving this awesome presentation about another aspect of astronomy that we normally aren't introduced to. Nathan, we look forward to an update, another presentation sometime in the future. Let us know what's going on. Yeah, on your awesome project. Thank you.
I'd be happy to do so.
Good. And Bob, thanks, Bob, for your presentation. What an awesome meeting this was, right? 2 great presentations. This is what the club is all about. So become an officer. Elections are coming up. Be a part of our leadership team and keep this great club going. What a fantastic club we got, all these great presentations. So help us keep it going. Volunteer for an officer position, and do that by letting me know. You can get on our website. Down at the bottom, there's the president's link down there. Let me know if you have any questions. Remember, October meeting, which is on the 15th, is when we formally accept the nominations, anything that has come in before, anybody that wants to do it, to volunteer during that meeting, that in a couple days afterwards, because November, we actually have the elections online. So guys, avoid the rush and do it tomorrow, right?
And if you volunteer, you're pretty much assured of winning the position.
Well, we'll see. I think we're going to have a few people interested in it, that's for sure. Keep this club going the way it is. And again, the previous officers are going to help, so don't be afraid about stepping up. Next meeting, October 15th. Tyler will be giving her presentation about planets orbiting K-stars and the superhabitability of it. So be sure that we watch her presentation come next month. So that's it. Any other questions that popped up? I'll give a few seconds. No, let's see. There's a question that came up. Rest up, Nathan. The conjunction will be over soon. Best to the Ingenuity team. And to EVAC for helping us to keep looking up. Yeah, that's right. Look up, folks. Keep looking up.
Thanks, Meg.
The sky is not a limit.
That's right.
Yeah. And of course, in the chat, we got a lot of thank yous, a lot of great presentations, both Nathan and Bob. Again, guys, thanks a lot. This is what the club is all about. You guys supporting it, it just makes it that much better. This premier club. So, guys, I will give the usual countdown. Give a moment of silence here. No one else jumps in. Okay, gang. 3, 2, 1. Bye, y'all.
Bye-bye.